So let us begin this last session of this FDP. Professor Pawan yesterday spoke about sequence-to-sequence models. Professor Pawan is associate professor at IIT Kharagpur, and we know him already. So today he will be talking about the current trends. So now the platform is open to Professor Pawan.
Thank you, Professor. So, yeah, so we are talking about current trends basically in deep learning for NLP. Uh, and I think you have got a bit of primer now from all the previous sessions on what are the basic frameworks on applying deep learning for NLP. And we will see, okay, what are the new things people are working on the last 1 or 2 years, and some of these are trends also for the future. And like yesterday, I would like that, yeah, I would like that you interact and ask your questions, and I may also ask questions to you. Okay, fine. So yeah, what about the current trends? So this is one of the picture you might have seen a lot of times that tells about why deep learning has been so successful, right? So, so 1980s, 90s, even I will say up to 2010, when I was doing my PhD. So that time the uh, main approaches were not neural network. We were using things like support vector machines and logistic regression and things like that, and they were giving better performance than neural models in many of the tasks. Now, what has changed is that, yeah, you have more and more data available. That is one thing. But now with all this architecture, new architectures and all, you can train a larger model size. And that is where we are seeing a lot of improvements. And now neural networks have surpassed the models. Very important thing here is that, yes, the data size has to increase. It has to increase. The computational hardware and other things are anyway there to support it, but the crux here is that I need a lot of data, right? Even if you talk about the problem that I discussed yesterday, and I think some of you had nice question about it, about this machine translation, right? And we are saying we are doing end-to-end training. I have no idea about the dictionary, that what is the translation of one word into another language. Still, if I have sufficient data, I have say 10 million sentence pairs. I can feed them into my sequence to sequence model, and I can expect to get some meaningful translation, right? And that has been possible through the use of these large networks and deep learning. So end-to-end training, so this is what I was calling as end-to-end training. So that has shown huge success for deep learning. But then there is this bottleneck that you need a huge training data set, right? So I need a huge training data set to be able to make use of these architectures, to be able to make use of all this compute, right? But is it something that is readily available to me always? So if I see even in English, a lot of tasks are there where I do not have sufficient data, right? So I don't have tasks where I have 100,000 examples. So you can take, okay, so think about you being a practitioner. So you being going to industry and working for making a sentiment analysis for your own product and how people are seeing that product from their reviews. You will get very little reviews. Maybe you will get 500 reviews. Now on 500 reviews, if you get data, how can someone expect to apply a deep learning model just by 500 examples and the ones that we are using for uh, end-to-end training? So this is for English, this is the situation for English, but think about the other languages, specifically for Indian languages. So there is even less data available. And there are like thousands of languages over the world and at least hundreds which have more than 1 million native speakers. So now the problem here is, okay, how do I deal with the scenario where I do not have sufficient training data set? Sure. And the second trend is yes, how do I make my model better? How do I understand it? It's just a joke. So I'll just read out. So yeah, this is a popular joke in MLs and especially in deep learning research. So yes, so this is your machine learning system. Yes, that is the question. And and yeah, this is, you can think of this as being me as telling yes, put your data into this big pile of linear algebra. That is my architecture, big architecture. Then collect the answer on the other side, and don't ask me what is happening inside. So just give me data, large data, and get your answer on the, as the output. And you will have the question, okay, what if the answers are wrong? What if the answers are wrong? And I will say, okay, don't again stare it. So what does it mean? I do hyperparameter tuning until you get good accuracy, and then you be happy with that. Don't worry why something is not working. So that is a popular joke, but this has also become a problem. Like, why are there talks about AI and ethics? Why are there problems about using deep learning methods for critical domains like healthcare? Why are people not so sure about using deep learning models in things like healthcare, things like uh, legal analysis, like predicting judgment of a case? It's a very critical scenario. Someone's life and death depends on this sentence. I don't know if I can trust AI for doing that. So one of the problem is that I don't understand the model so well that I can say, okay, why is this particular prediction happening? So excuse me. So so these are the two things I will talk about mainly. One, okay, how do I lower the requirement of task-specific data set? That I might have hundreds of tasks. I might have different languages. Each language I will have so many tasks. Now, who will sit down and annotate data set for me for everything that I'm doing? So can I lower the requirement of task-specific data set? So what are the ideas, some of the ideas around this? That I am doing name and recognition for Telugu language, but I don't have sufficient labeled examples. What do I do? I want to translate between English and another language, say Nepali, and I don't have sufficient parallel data. What do I do? So, so this is one very, very important trend, and this is something that is worth going on. So it will go at least for another few years. So how do I lower the requirement of task-specific data set? And the second one is, how do I interpret the output of neural models? How do I say, okay, this is why my model has given this output? And yeah, with that, you can do many more things. Okay, I don't agree with the analysis, so I don't agree with the output. You can say things like that. Sure. So now let me start with the first part, lowering the task-specific dataset requirement. So idea is that yes, in machine learning, in NLP in specific, I have lot of tasks. And for each of the tasks, I may have different types of data requirement. But can I leverage on something else than just annotating, just doing blindly, okay, I have this task, I need 100,000 labeled examples, and that's how I will work. No. Can I do something else? So one of the very important idea that came is started from 2017 itself is huge contextual representations. I'll talk about that. What do I mean by contextual representations? And with that, there were ideas about pre-training, large pre-trained language models that have become like the de facto models in NLP now. So if I have to do anything, I'll just go and say, okay, can I apply BERT on this? Yes. So the ideas came from contextual representation, that can I have large pre-trained language models that I can use. Then can I also use multitask learning, that I will briefly tell. Maybe I will not be able to touch upon this, but also use of unlabeled data set. I have a lot of data set that is not labeled, nobody had annotated. But can I do something with that? But when I am saying I won't be able to touch upon that, we have already talked about this, right? So can someone tell me how in NLP we are using unlabeled data set? What are the different ways we were leveraging on unlabeled data set already in NLP? Unlabeled means no annotations, just raw data from the web. Can someone tell me how we were using this already in uh, the whatever we talked about? What are things we are doing with unlabeled dataset? What about word to vec? And what about RNN language model? They don't need any annotation. You just feed raw data and you learn word to vectors. You feed raw data, you learn language model. So that's where we were using unlabeled data set already, right? And that actually was helping a lot. You can use a large corpus, train your word vectors, and then use them for your new task. You don't have to retrain them again. They're already trained, right? So this idea was there somewhere that yes, I can use large unlabeled data set for some particular task like word vectors or language model and use them for further tasks. So yeah, now let me take a cue from whatever we did yesterday. So we talked about machine translation. Now, and I said, oh, you need a large parallel data. So this is important, large parallel data set. That means I have a sentence in English and a corresponding translation in, say, Hindi. And I need like at least 1 million such pair. And then I will be able to feed them to my sequence to sequence architecture. And that I expect that it will be trained, it will learn all those 5 matrices, and will produce a good enough translation given a new English sentence. Now, what if I do not have 1 million parallel data set? What can I do? So what can I do differently to be able to train a machine translation system from uh, English to Hindi? So the idea comes is, okay, I don't have parallel data, but I will have monolingual data. That monolingual data may be abundant for languages. For example, you can take Wikipedia articles, and they are available in so many languages. You can crawl specific Wikipedia articles for a language. So I can take monolingual data for English, I can take monolingual data for Hindi. Now, what can I do with that? Right? So I know that if I have to train a machine translation system, I need to have an encoder-decoder architecture. Encoder, I have 2 matrices. I had U and W, and decoder, I had U prime, W prime, and V. So these are the matrices that I was training together with this data. But now I can say, okay, fine, I don't have parallel data. So I will treat it as a slightly different problem. What I will do, I'll train my encoder and decoder separately. So because for training encoder, what I'm training, how to encode the sentence of language English. And that I can do by just training an RNN language model over English dataset without worrying about the other language. So I can separately train both encoder and decoder as language models directly, right? And we learned yesterday how we actually train language models. And I have separate training of this encoder decoder. So that means all these matrices, they are already trained somewhat. I don't have to start training from scratch. And that is a very big idea. Okay, yes, you don't have to start training from scratch. They are already trained with some data. Now what you do, now you take the parallel sentences. You will have some data. You may have say 10,000 sentences. And that is much smaller than 1 million. But now what you do, you take these sentences and fine tune your overall architecture. So now you fine tune. So these are already trained, but you again allow their weights to change, but the loss will be from this parallel sentence now. This parallel sentence will give you the loss, and that will help you backdrop on and change. And you see, that is the reason, I don't know whether you have come across that. You will find in Google Translate or some other cases, if you give an arbitrary sentence also, it will give you a very good looking sentence in the other language. Even if the translation does not make sense, but the sentence output may make a lot of sense. And that is because a decoder has been trained separately and it knows how to generate a good sentence, right? But the mapping, the input to output mapping, that is what is being learned from this bilingual data. But but you see, if you are training it together, you have to learn a lot of things. Not only the mapping, but how do you output sentences in the target language? What is the correct sequence order? Everything you have to learn from the same parallel data. But now what you are doing, you are dividing the task into multiple things. Okay, let me learn that separately by using encoder decoder trait, and now apply parallel data and learn the mapping between the two languages. So yeah, so this is something from just from yesterday. Now let me talk about the contextual representation part and how it became a very important idea in the field of current trends for NLP. So you had a very good session on word to vec, right? So you know how to represent word vectors. You know what to act, and there are other variations might have been covered like glove and etc. Fine. So what do they do? Given a word, they will give you a word representation. Yes. Now, what is the problem with this representation? Can someone tell me what is one problem with this? I can feed a lot of data and I can learn representations, right? But there is one problem with this. Just tell something, even if it is not a problem, it's all right. If you are thinking about it, like what can be one problem with this word like this? The way I have learned it. Think about the language. So what would happen? You will give a feed a vocabulary, and for each vocabulary, each token, you get a word vector. I have a word vector, some d dimension. Right? What is the problem? Say I have one of the word is bank or bat. Do you see a problem? I am learning a representation for bat or for bank. A single representation. Do you see a problem there? Okay. So let me give you sentences. Suppose take these two sentences. Open a bank account or on the river bank. I have a single representation for bank. Does that look all right to you? Or do you see some problem? Embedding are supposed to give me some meaning of the word, right? What are you seeing here? What is one problem?
Uh, Basically, bank has two different meanings.
Uh-huh,
One
uh-huh.
is one is a normal bank where we do transactions, and the river bank is also there. So this might give conflicting results.
Yes. So what is the problem? Can you now tell the problem? What is the problem? That I'm learning a representation. For a word, I have a single representation. But in language, words have meanings and not just one meaning. They can have different senses. Like this bank, it can be like the financial bank, it can be the river bank. And the two are not the same because in the river bank, I cannot go and deposit my check, right? Uh, Similarly, word like bat can be the cricket bat, it can be a mammal, bat can be as a mammal. Season, can you think of meanings of season? What are the two meanings of season? You can tell me. A popular meaning of season that has just come up after that, yeah, that has come up recently. Okay, yes, season, yes, festival season. One of the things could be yes, spring and other seasons, fine. But what is the new meaning of season that has come up? Season 1, season 2, and all. Do you remember anything from this? All this web series and even like you will have the season 6, season 1, season 2, and so on. So the words have meanings and they keep on getting new meanings. Okay, so I cannot capture everything in a single vector, and if I am attempting to capture in a single vector, that is going to create problems. So what we might want we would like that in the two contexts that the bank is occurring, or open a bank account on the river bank, I should have different representation for bank. So here it is a different vector than here. So, and depending on the context, the meaning should change for a word. How do I do that? How do I do that? Any idea? Like, how would I handle this? Depending on the context, I should have different meanings of a word. How would I handle that? Are the language models already doing something like that? Are the language models already doing a context and specific meaning? What would happen if you pass these two sentences through a language model? What would happen? And let's say I have a single representation for bank in both the cases. Same representation. Okay, this is same. Is there some way my language model can give me different contextual meanings of these two words? What can be a proxy of the contextual meaning of the two words? Let's say they have the embeddings are same. I can say, or I have whatever embedding I have, open a river bank account, I pass it through my hidden states, right? And this representation. Similarly, I pass it through hidden states and this representation. What do you think? Will they be the same? Say R bank and T bank. Even if they are same, these two are same. Will R bank and T bank be the same here in this figure? So you see, you are passing different words, there are different embeddings, even if the matrices are tied up, matrices are same, whatever comes here is going to be different, right? Because they are not going through the same sequence. So the language model anyway gives me this facility that I can pass any sequence through a language model and the hidden state will give me a contextual representation. So it's already giving me a contextual representation. Right? So if I pass this, my favorite season is spring, and I look at this particular hidden vector for any word, that is giving me a contextual representation. Okay. Now, very good. Now we have it. So how can I leverage that for a new task? Suppose I am doing a task like named entity recognition. Suppose now I'm doing a task like named entity recognition. That is, given a sentence, find out what are the names in that, right? How would I use that? This particular idea that, okay, language models give me contextual representation, but word vectors inherently are not contextual, right? So how do I combine these two ideas? So that's where this paper Tag LM, Peters et al. 2017 came up and became, it actually became very popular. And they had a subsequent paper in 2018 that I'll talk about. That was further, that is actually much more popular. So what they argued that, yes, I want word meaning in context, but you see, that's where we are coming to. The task specific data set is very, very small. Suppose I am doing NER problem, named entity recognition. I may have say 10,000 sentences that have named entity tags available. I have to train my model based on that. Now I cannot hope to learn even the word census from this small data, right? So can we now leverage on unlabeled data set? So can we use a semi-supervised approach where what I do, I take say large English Wikipedia or some text and I train neural language model on this large unlabeled data set and use the hidden states there as my contextual representation, right? And this was like a very interesting idea. So you do something like that. You do something like that. So you have this large unlabeled data set, right? And this is actually really large for monolingual data set. Now we know how do we use that to train word embeddings. Right? We know we can use word, apply word to vec. We also know how to use that to train recurrent neural network language models. Right? Fine, very good. Now once I have got both these, I have got word vectors, I have got language model. What I will do, given a sentence that is task specific. Now this is for my NER task. I have to find out what are the name entities. Like here, New York is located. The name entity is New York, right? And you see your final label is beginning of location, is a location, and end of location. The other labels for this these two words. So I want to do a sequence labeling. For each word, I want to do a classification. New is beginning location, York is end of location, outside, outside, and so on. I want to do that. Before using this contextual representation, what I would have done, I would have just fed the word embeddings for each word. But then it will not give me the contextual meaning. Like new, the word new is like so common. It's new something, right? But New York would have a separate meaning altogether. So I feed the word embedding, I concatenate with that the language model embedding. So what I will do, I'll pass New York is located through a language model. Because my language model is trained, I'll pass it through language model and use the hidden states. So this hidden state that I'm getting is what becomes my LM embedding, language model embedding. I concatenate that with the word embedding and then give as input here. So more details. So for example, yeah, so this is just telling the same thing in further details. So you have this input, New York is located. So what you do, you are anyway passing it. So you can use the embeddings, and even in practice, you see when you are applying any recurrent neural network, you try to use multiple types of embedding so that your model is not constrained by the only type of embedding you use. So I can give, say this can be my word to vec. And I can also feed as input something that is learned based on characters. So character label embeddings, they are like character CNN. I can give a fast text embedding. So I can feed some embeddings and concatenate them. So I'm putting that embedding as my input. Okay, and then this is being used to train my bidirectional RNN, right? And this gives me a hidden state, H11, H21, and so on. We know that, we know how to get this hidden state. But what is different now, the different here is, I separately pass the same sentence through a language model that is already trained, that is pre-trained, okay? This is the training phase for NER, training of NER. But I'm using an RNN language model that is already trained. So that means I can pass a sentence, I can get the hidden embeddings, right? And I can use a bidirectional one, so I can have forward language model, backward language model, get both the hidden states and concatenate these. Now this hidden state, I'll concatenate with the current hidden state of my language model. And this is what is used to either go to higher label or predict the output directly. You can use that now to predict the output. So what has happened now? Your hidden state captures not only your individual word embeddings, but also your contextual word embeddings. And that are being used for predicting your final text for this task. And that people have seen has lowered the requirement for task-specific training data set a lot. So that was just one idea, and then this is again their subsequent paper from 2018, and this you might have heard the name ELMO. So this is nothing but embedding from language models. That's what is ELMO. So this was published in NACL 2018. So what ELMO does, so it learns task-specific combination of bidirectional language model implementations. So we were already doing that. So the idea, it was building on the idea of the previous paper of Peters et al. 2017. So their own paper. So what they do now, so they do something different. They say, okay, when I'm training an RNN, right, as a language model, I can use multiple layers. So I assume you have seen that when I'm training a language model, like for a word, I can actually have multiple layers. So this is, suppose this is my first layer. Superscript is telling me the layer number. So, but now I can keep on stacking multiple layers. So I can say, okay, I'll put it through another layer, H1, 2. And this can get input from H0 to H2 to and H3 to and so on. And I can keep on stacking multiple hidden layers in RNNs. And then final hidden layer will go to my directly my output. Yes. So this is all possible. So what they said, okay, fine. Because I have multiple hidden layers, so from the RNN language model, given a word as input, I can get context as multiple contextual representations at multiple levels. I can get it at layer 1, layer 2, layer up to whatever k layers I have. And why don't I use all of these instead of just using the final one? Their 2017 paper used just the final layer hidden state. They said, okay, why don't we use everything? Not only use everything, but say, okay, how much importance do I give to a lower layer compared to a higher layer may also depend on what is my task. Like if you're doing simple tasks like part of speech tagging, what is the grammatical category of this one? You may not need a very high layers. But if you're using complicated tasks like co-reference resolution or doing question answering and all, you may need a high level layers. So that's what they did. They said, okay, suppose I'm using L layers. So let's use the hidden state of all of the L layers along with the word embedding, that you can call it the 0th layer. So this is my HKJ, all the J layers. And now my final representation that I'm taking from this ELMO, the pre-trained language model, is nothing but a weighted combination. So just a weighted combination of all these hidden states. Okay. But what are the weights? And they are being tuned task specific. They are normalized, softfix normalized, so they add up to 1, but they can be different for different tasks. And further, they also multiply this whole thing by gamma task. It a scalar parameter that says, okay, how much would this ELMO be important for this task? So these are two things they actually use. So yeah, this is a popular ELMO figure. Yes, you might know the cartoon series from which it was taken. So that's what they do. So again, if I go back to the same example, actually using roughly the same figure to explain this. So New York is located, fine. You do the same thing. You get the embedding, you get the hidden states, H11, H21, fine. But now pass it through the language model, get the hidden states at all the layers, And now from there, compute a task specific representation. Okay, and that you concatenate with this. Okay, and that further goes for this particular task. And also you have a gamma involved. So in their experiment, they just work with 2 layers. So this L was 2 that they were using. And what they found was interesting. So the 2 BioSTM layers that they had differentiated meanings, and they were useful for different types of tasks. Like the lower layer was good for lower level tasks like part of speech tagging, dependencies, named entity recognition. Lower layer was good enough. But if you are doing high level semantics like sentiment analysis, like that requires further, that requires you to understand what is the, because there can be sarcastic sentiments, right? So there can be a lot of different things. Semantic role labeling, question answering, natural language inference, or semantic similarity. They were had to use a higher level layer. So, and that was very interesting that yes, lower level layer are good for this syntactic task, but if you are going for semantic task, better to use a higher proportion of the higher level layer. Another reason why this Elmo became very, very popular was till this point, all the models used to give a good performance for a given task. They were trained for a task. Like NLP research were all about, okay, I am training a new model for named entity recognition, or I am training a new model for part of speech tagging for this language. Now, what they did differently is that, okay, I am giving an architecture here, and now I can use it for question answering, I can use it for sentence similarity, I can use it for NLI, and everywhere they were showing improvements. And this created a buzz in the community. So that's why Elmo has been very, very popular since then. Another very interesting idea came around the same time was Howard and Ruder 2018 paper, is the universal language model fine-tuning for text classification. Again, very interesting idea. Building upon whatever we have discussed, but you will see there is something very unique to this. So idea was that, yes, I have a source label data set and I can create a source model, but how do I transfer that knowledge to a new label data set? That can be different. So how do I start using some sort of transfer learning? And they did it for text classification. Okay. So what was the idea? So if you see the steps, they are something that we already seen, but you see the sequence is what made it very interesting. So what they do, they train language model on a big general domain corpus, right? So you can take, like I'm always repeating this, Wikipedia or gigaword corpus, you can take any large corpus and say, okay, I train my language model on that. Fine, so this part is nothing but your language model training. And that can have multiple layers. So you can have multiple layers, and finally you are predicting. This softmax layer is nothing but predicting the next word, right? And you keep on getting the new word, and it's like you are going back. Okay? So that's how you should see this. Fine, we know that. We know how to train a language model. But then the next step is tune language model for target task data. It's not labeled data. So it's not labeled data. So because language model is only the task of predicting the next one. You say, okay, this may be Wikipedia corpus, but now suppose this may be your biomedical corpus. Suppose you want to do something for extracting information from biomedical articles, or it may be about, it may be a text from Amazon reviews. I am doing a task on Amazon reviews. So I say, okay, I will take this data as it is. I'm not, sorry, not data. I'll take the model as it is, whatever I have trained, and fine tune it. Fine tune meaning I will again retrain the weights. Okay, again retrain the weights. I do fine tuning on this target data set. Fine, I do that. All right. So this is a sequence. I now have original language model that is fine tuned on my target data set. Now comes the labeling part, target labels. So the target task can be different than language modeling. Language modeling in itself is not a very, very, important task, but the underlying architecture is very important. Important tasks are like text classification is important. I want to do sentiment classification. That's important task. So I take the data set, fine tune my language model on that. Now I do something for the task. So now you see I use the same model, but instead of predicting the next one, so this is in black. So that means I don't do anything. So forget about this part. Just forget about this part. Now you add, because I'm doing say, let's say binary classification. So I add these two neurons and say plus minus, positive, negative, and I'm now training these weights. I'm training these weights. These are new weights, right? They were not there. I'm training these weights, and this I'm assuming is already trained, but I still allow them to train a bit. But that also I say, okay, the initial layer you don't train so much. This one you train slightly more, slightly more, slightly more. So it's an idea of freezing some layers, unfreezing others, right? And by freezing, I mean you don't make your gradient to go back to that. It does not update. But unfreezing means you allow some slight gradient to flow, or your learning rate is very, very small, and that you use that. So, so this was the idea of universal language model fine-tuning. Yes, have a large language model, fine-tune on your target data set, then again fine-tune on your task. Target data set, target task for the data set. And this is what actually gave them, you see, the transfer learning capability. So this picture shows the capability. So on the x-axis, you are seeing the number of training examples for the target domain that you have to use. And y-axis, you are seeing the validation data set error rate. So you know if it is lower, it is better, right? So lower the better. And if it is lower on small training examples, this is what you need. If I can achieve a low error rate on very small amount of training examples, I like my problem is solved, and that's what they showed. So the blue curve is what happens if you train from scratch. Like you're doing end-to-end training, and if you see if you're using 100 200 examples, huge 50% error rate in classification tasks, but maybe it's like nothing has been trained, right? But even if you use 20,000, it comes down. It comes down to something like 10% error. Yes, but now see the universal language model, it should be FIT here, fine tuning. So what they have shown, even with 100 200 examples, they are able to achieve better than whatever they could do with scratch, even with 20,000 examples, right? So so yeah, this was very, very interesting. And of course, if you give more examples, it does much better than this model. So the gap is huge for a small number of examples, right? And that's what they achieved by as a transfer learning. And of course, the starting from then, it's all about building more and more complicated models, scaling them up, right? So after ULM, this universal language model fine tuning came GPT, the first version, that was in 2018. Then came BERT, and then came GPT-2, and now you know it's all about GPT-3 that you hear. It's GPT-3, yes. And what you see, they are large and large models. So they are trained with more data set, more number of epochs. So this particular model, ULM Fit, was just trained for 1 GPU a day, running a single GPU for a day. But this GPT was as if you are running single GPU for 240 days. And similarly, all these models, they have more and more compute requirement. But they have also shown better and better performance. And one thing that is important is that this Elmo, the model that we talked about, this was not based on transformers. This was simply based on this recurrent neural network language models, right? It was just using RNA language models. But all the other models like GPT to BERT to GPT to XLNet and ERNIE, etc., that are very, very popular nowadays, they're all based on transformer models. Okay, and I think transformer I anyway covered today. So transformer has been a very, very basic idea of, because how transformer helps, it avoids going to recurrent direction, and that's where you can do a lot of computation. You can parallelize the computation. So all these models use that architecture for training. So I'll briefly talk about BERT, that is very, very popular. And BERT stands for bidirectional encoder representation from transformers. So you see, it is actually an extension of transformers, but it uses some extra ideas. And yeah, say this is again from the same show from where Elmo was taken. So you have BERT. An idea was taken from whatever you have seen earlier. So this is idea taken from Elmo, idea taken from ULM Fit, idea taken from transformers, but they had their own new ideas also. They had their own new ideas. What were those? So yeah. So first of all, the one problem that they solve with the language models is that whenever I'm training language models, I only train it from left to right, yes, or I train it from right to left. So I can have a forward language model given the previous words x1, x2, x3, predict x4, or given the next words x4, x3, x2, predict x1. So you can have a forward language model, you can have a backward language model. Okay. When I try to understand language, I have to make use of both the left and right context, right? So for example, if I say the movie was terribly good. I don't know whether people use that, but let's suppose I say this, the movie was terribly good. What do I mean? What is the meaning of terribly here? The movie was terribly good. What is the meaning of terribly? Although when I say terrible, I generally have a negative sense. But if I say terribly good, I'm just making, okay, it was actually good. It was actually good. But I won't understand that until I have seen that there is a good towards the right. Right? So I need to have context both from left and right to be able to understand a word. Now this is what is the capability that this bird tried to see. Okay. In general, for language models, I cannot use bidirectionality, but is there some way I can incorporate this? So this is what is a unidirectional context. I start giving a sentence like open a bank account, and start predicts open, open predicts A, and A predicts bank. Now, can I use bidirectionality here? Can I say, okay, why don't I use a bidirectional and recurrent language model, BiRNN as a language model? Can I use that? Can I say, okay, let me predict the next word from seeing these two contexts, these two hidden strings? Can I predict the next word? What is the fallacy there if I start predicting the next word at this point? Bidirectional means at this point I have seen the left context, I have seen the right context, right? I have seen both sides. But if I have seen both sides and I'm trying to predict the next word, that does not make sense, right? Because I've already seen that word. So if I'm predicting that, I'm not going to learn much because I've already seen that as my input. So this is the problem. Words can see themselves if I try to give a language model that is bidirectional. So language models were inherently unidirectional, either forward direction or backward direction. You do not say, okay, I have a bidirectional language model. But what happened in this BERT? The idea that they came up with something called a masked language model. So they said, okay, I'll take the sentence, the input sentence, and I will mask, some of the words. I'll mask some of the words. Like for example, here, the man went to the store to buy a gallon of milk. So if I take this sentence, the man went to the store to buy a gallon of milk. Okay. So what I do, I mask certain words. That means I uh, remove some words from the input. Yeah, I remove some words from the input. And then what I do, I try to predict that, right? So I'm not seeing that input, I'm trying to do fill in the blank. Say, okay, what should come here? And that's where I try to use the other architectures like transformers. Okay, now I use all the other words in the sentence to predict what is the masked word. So this is what is called masked language model, right? This is in contrast with the normal language model where I am given the previous context and I predict the next word. So this is a new task that they came up with, and they said, okay, with mask language model, I can actually use context from both sides and predict a word. And that's what they use for training. And again, masking, because if you see, if you do very little masking, there's not much training that will happen. And if you do a lot of masking, like if in a sentence you mask like half of the words, there's not much context. So you need to keep a balance between the two, that I should use some percentage of words for masking, and I use the other context to predict that. So they use something like 15%. They use 15% of the words as masked and then try to predict those. Another task that they added was called next sentence prediction. That is, okay, till now, all the previous language models, they didn't go to sentence level. They said, okay, I'll try to predict the next word. But they said, okay, can I understand whether my language model is having some more, it's learning a lot about the sentence structure. So they said, okay, given a previous sentence, like the man went to the store, and an example sentence like this, he bought a gallon of milk. Will my model be able to say that, okay, can this be the next sentence? Is it the next sentence? The man went to the store. Is it the next logical sentence to say? He bought a gallon of milk. And we will say, yes, that looks logical, right? But what about this? The man went to the store. Penguins are flightless. Wow. So individually they may be fine. Individually they may be fine. But sentence be coming out of after sentence, and we will okay, wait a minute. So this does not make sense. This does not make sense. So now they said, okay, this is interesting. So why don't I use that for my training? And this, if you think about it, this again you can get from a large data set, say Wikipedia. You take Wikipedia, sentence pairs, and say, okay, I take sentence one, the next sentence is the logical next sentence that I know from the data. Now replace it with a random sentence, S1 and a random sentence, R2, that has no connection with this sentence. And you create artificial data set. You say, okay, this is, if I have these two pairs, S1 and S2, the answer is yes, this is next sentence. And if I have the pair S1 and R2, the answer is no, not next sentence. So they created data in this form. Then they said, okay, I have these two ideas, mask language models, so that I can use bidirectionality in my language model itself. Second is, I do next sentence prediction, popularly known as NSP, next sentence prediction. Given the previous sentence, can I predict this thing is a next sentence or not? And together using that, they trained their BERT model. So generally in their BERT model, what they did, so it's not concatenation, this is an addition of 3 embeddings. So they will take 3 different embedding types and they will add it. Position embedding, same that were in transformer, they just take the same things from the transformer. Then segment embedding is whether it is part of sentence 1 or sentence 2, because they have 2 sentences. Say, my dog is cute, he likes playing, 2 sentences, right? And there are other details like, okay, the vocabulary that they use is something called word piece. Word piece is a nice idea to take care of this morphology. You know the thing like play, played, playing. So they are all morphological variants. Now it becomes difficult to learn embedding for each individual word. Especially think about languages that have rich morphology. Like Sanskrit has very rich morphology. This will have a noun giving you 72 different forms, a verb giving you sometimes even 90 different forms, or even more. So I don't have data to learn embedding separately. So what I do, I try to break them into morphemes. So I say, okay, played here and ing is here. They are 2 different tokens altogether. So this is actually word pieces that you might have seen in one of the talks, but yeah, otherwise you can look it up. So what it tries to do, it takes the input vocabulary, tries to break into the manageable vocabulary by breaking long words into smaller words. Especially morphological variants are one of the things it takes care, like playing. So they use the word piece vocabulary from the sentence, and now they are feeding this. So they are feeding position embedding, yes, just like transformer. Segment embedding can be as simple as one hot vector, but they use some random embeddings for both. segment A and B, and then the token embedding. What is my token of the sentence? And they feed it, and they together, just adding this together becomes your input. Now this is the input that goes into the BERT. And BERT is, again, there are various variants. There are 12 layer variants. There are 24 layer variants, right? Base model and large model. So now they apply uh, this BERT model. So if you see here, what they will do, so suppose I have two sentences, sentence A, sentence B, and they are fed by using these two tokens. They are very specific in BERT nomenclature, CLS with before the first sentence and separated, the sentence separated. They feed it and they get this embedding as we saw in the previous slide, just addition of three embeddings, positional, segment embedding, and the token embeddings. And inside you see are all this transformer and BERT interplay that is happening. And finally, this is where they get the final position. And they use it to do both the tasks. Like they train it with both the tasks. One is masking, so what predict the mask word, and second, predict whether sentence B is the logical next sentence of sentence. So they have this as a simple classifier, and here they are doing a prediction. That they do. This is how they do pre-training of BERT. That is BERT pre-training on large data set. But once they have pre-trained BERT, now they can do the same idea of fine-tuning. So now what they do, they say, okay, I'll take this architecture as it is. I'll take this architecture as it is. Actually, forget about even this part. I'll take the underlying architecture as it is and use it for any other task, like NER or squared. Squared is a popular task for reading comprehension. Use it for different tasks. In reading comprehension, what happens? You are given a question, you are given a paragraph, you have to find out where in the paragraph the answer lies. So it will be some start and some end. It will start somewhere and end somewhere. So you have to predict what is the start token in the paragraph and what is the end token in the paragraph. So they said, okay, I forget masking now. I just use the final output to predict what is my start and end point. Similarly for other tasks. So this BERT is very, very popular. People just take this pre-trained BERT. So you take pre-trained BERT and fine-tune it on your task. So you can have a task like name entity recognition. You can have a type task like natural language inference, sentence similarity. Sentence similarity, you can feed the same architecture. Instead of classify NSP, you can have is it similar or not? Similar sentence or different sentence? Or does it entail the sentence or not? So that is how BERT has been used. And not only that, BERT, this is the generic BERT. People have applied BERT and trained on various domains. So you have BioBERT. So BioBERT, what they have done, they have used the same idea of BERT training and applied it on large biomedical data sets, say PubMed articles. Download all the PubMed articles and train this BERT. And this actually works better. Right? So there is BioBERT, and there is this, recently there is this eBERT came in. So you take all the e-commerce like Amazon reviews and so, and train your BERT model on them, and so on. So then there is this idea about multitask learning. And so the simple thing there is that, yes, so whenever I'm trying to learn something new, I will utilize whatever I have learned. So if I know linear algebra, so when I'm learning deep learning, I will apply my knowledge of linear algebra to deep learning. I don't have to learn again from scratch. So the idea is that, okay, I have so many tasks. Can I use the knowledge I have gained in one task to improve performance on another task? And this is a common example. You could say, okay, a baby may first try to recognize the faces of like parents and other people around, and then it uses whatever it has learned. Okay, this is how I recognize faces, to say, okay, how to recognize objects and so on. Same way for language. You can say, okay, I have learned how to recognize whether this is a noun or a verb or something. I've learned that a single word, noun, verb, and so on. Can I use this knowledge already to learn, okay, is it a name? Is it a name? Is it a location? Is it a person? Yes. So can I use whatever I have gained in the previous task? So, so that is what is multitask learning. So there are two models, multitask learning models that are very, very popular. One is called you do hard parameter sharing, another is soft parameter sharing. What is hard, what is soft? So hard parameter sharing means, so across multiple tasks, your underlying parameters are the same. And soft means they are tied by some constraint. For example, they don't deviate too much from each other, but they are allowed to be different. Okay, so this is how the architecture for a hard parameter sharing looks like. So think about doing different tasks. For example, one task could be I feed a sentence, and task A could be okay, find the sentiment. Find the sentiment for the sentence. The second task could be say find the topic. Topic could be okay, is it about politics? Is it about entertainment? And third task could be okay, uh, think like okay, so something can be as different as is it a polite sentence or is it rude? Okay, so the task can be like that. So so I can have multiple tasks. Now how would I handle in general? By my normal deep learning, I just say okay, I have three tasks: sentiment analysis, I have sentiment analysis, topic classification, I have politeness detection, is it polite or not, or maybe is it a sarcasm or not? Okay, it can be a task. I will do it separately and I will train separate models for that. But in multitask learning, what would happen? So you say, okay, I'll feed a sentence. I'll have some layers that are common to all the tasks. So I feed, say, RNN language model. Think of it like as if an RNN language model going for multiple layers. And here you're getting H1, H2 up to Hn. If you are inputting X1 to Xn, you're getting those hidden states. Now, what you're saying, okay, if you're doing a single task learning, you will just take this approach. So we'll take these hidden states and do something like either just use the final hidden state for doing task classification, or do some fancy things like doing summation of HIH and then passing it through a another layer, maybe multiple layers, and then doing a softmax layer finally. That's what you will do. But in multitask, what you will do, okay, I am this representation that I'm getting, H1 to Hn. This I will say is common to all the tasks. But now from here, I have task-specific layers. So I have task-specific layers. So when I am training, I'm training such that whenever I'm computing a loss for task A, it backprops here, fine, but it backprops to all the previous layers also. Similarly, task B, it backprops to all the layers. And similarly, task C backprops to all the layers. And this helps that these representations become very, very strong. They don't have to be trained separately. I have now these repetition trained from multiple tasks. And whatever I have learned from sentiment task, I'm also learning for topic task. See, this will be helpful if you have, say, different data sets for three tasks. You don't have the same sentence label. You can have, say, think about, you have 10,000 sentences for sentiment, another 5,000 for topic, another 2,000 for politeness. And this is how you will have. Maybe you will have more for topic than sentiment, something like 15K for topic. So 2K for politeness detection is very, very small. But can I leverage on the 25,000 sentences that I had for sentiment topic to learn these layers already and then go to this task-specific layer? Okay, that is the idea. So I leverage on other tasks. Okay. Similarly, there is soft parameter sharing where you say, okay, think about independent architectures. Fine, it's a single task, task A, task B, task C. But what you do is something called parameter time. So you have, say, okay, the parameters of this layer and parameters of this layer, they do not uh, deviate too much. They are very similar. How do you put a constraint like that? That the parameters that I have in these two layers, they're not so different. How can you put a constraint of that form? Any idea? How do I put a
Taking
constraint? Mhm.
taking mean square error difference between the weights.
Yes, yes. So I can take the weights, weight, parameter weight here, weight A, weight B, and I take weight A minus weight B. Square. And this I can add as a regularizer. This can be my regularizer during my training. And this I do for all the parameter time. I just keep on adding sigma, all differences of parameters. So theta, task A minus theta, task B. L2 norm, let's say L2 norm. I add regularization. So these two are very popular architecture, hard parameter sharing and soft parameter sharing, and have been used in multiple NLP problems. Okay, finally, I'll say a few things about analysis and interpretability. So, so the fact that these deep learning models work for all these tasks is actually very perplexing. That how do they work? How are they able to give an answer? Suppose, uh, so this is reading comprehension. I was talking about reading comprehension. So what you see, you have a question. How did some suspect that Polo learned about China instead of by actually visiting it? And you have the paragraph. And the answer is there. And answer is actually highlighted. I mean for you, but for the model, the answer is not highlighted. And the model gives me this answer through contact with Persian traders. So this is the output I'm getting, and that is actually the correct answer. Now, how is this model able to analyze this whole paragraph and able to come up with an answer like that? Right? This is very perplexing. Similarly, like this is something we were discussing yesterday. How is it that I'm just feeding the sentence, one sentence in language one, and the corresponding sentence is language two? I'm feeding a lot of pairs, and it is able to learn how to translate, right? Without being able to explicitly tell this, okay, this is how you translate. No, just give me data and it is able to do translations. Similarly, is it a valid next sentence or not? So one thing we can say, okay, we are happy with whatever it is giving a good accuracy on the test set, but we may be more critical about it and say, okay, can I also do some analysis? Can I also interpret my model output? Can I say what my model has been able to learn, what it has not learned? Can I say whether my model is able to make use of this information at all, or it is not able to make use of this information? So this is a field of analysis and interpretability. I'll just touch upon briefly on few of the things here. So, so first of all, how do I understand the language capabilities of a model? The answer can come from, okay, how do I understand the language capability of humans? How well they have understand language. So this is one of the issue I see a lot with the students writing. Like many of the even senior students make this mistake. So, simple thing, the chef who made the pizza, right? And pizzazz, who made the pizzazz, and you have to put an edge, right? But sometimes people put R, and they just see the previous word. Okay, after pizzazz you will have to put an R, but this is not correct, right? Because this is depends on the subject. The chef who made the pizzazz is, right? The chef who made the pizzazz R looks weird. It looks wrong. So we try to see for humans, we try to give such confusing pairs and see, okay, whether they are able to give me the correct answer. Whether they are able to say, okay, this is a correct sentence and this is an incorrect usage of. in the next sentence. Next. What? So this is the agreement in number. The chef should agree with this number, H versus R. Similarly, if this is the verb, this is the subject. That agreement I should capture. So let's talk about this, capturing this number. Now, this is what I will do for humans. Now, can you think how can I use this idea to test the capability of my neural language model? So what have my language model learned? Can I use that to test that? What can I do? In our language model, how do I capture what they have learned? So it is all captured by the probability. Remember, in language models, language model is what it gives me the probability of a sequence, right? So if I give it two different sequences, the chef who made the pigeage is the chef who made the pigeage are, it will be able to tell me the probability of both the sentences. So suppose if my language model gives a higher probability to the acceptable sentence, and think of these two sentences as a minimal pair. So this is a minimal pair. In a minimal pair, there is an acceptable sentence, another is unacceptable. Okay, so suppose I have a minimal pair like that. My language model should give a higher probability to an acceptable sentence than an unacceptable sentence, right? And that makes sense. That should happen ideally. So I use this premise that, okay, a language model should assign higher probability to the acceptable sentence in a minimal pair. And now with that premise, what I do, I create a lot of such minimal pairs. Okay. So then what I do, I gather or construct a test set of such minimal pairs which require some specific aspects of language understanding. For example, here it was all about understanding the number agreement, that subject verb number agreement. That subject is here singular, chef, so the verb should also be singular, H, not R. So this agreement I am trying to capture. It's my language model capturing it. So what I will do, I will create a lot of such examples where I am testing this particular agreement. Okay, and now what you will do, you will run your language model on these pairs. So you will say, okay, first sentence, second sentence, one is correct, one is acceptable, another is unacceptable, and you will run your language model on both and see what is the output. Is the language model saying this is having a higher probability than this? Then the answer is yes. But if it is saying this, the second one has a higher probability, then the language model is not saying good. Okay, so like in this case, suppose out of 4, in 3 cases, language model gave the high probability to the correct acceptable sentence. But in the 4th one, it gave a higher probability to the unacceptable sentence. You will say in 75% of the cases, my language model is doing fine. So this is how you can test the language comprehension capability of your language model. Like here, the chef who made the pizzas and talked to the customers. You can say, you can keep on increasing attractors. So we call this attractors. So you see, this is the subject, and the verb number should depend on the subject. But if in between there are some attractors, so like nouns, pizzas, customers, and they are attracting the language model to give a wrong answer. So pizzas will possibly force language model to give an answer like R. Customers again will force language model to give an answer R, right? But the language model should be able to look at the chef and give an answer. So you can do experiment by keep on increasing the attractors. I may have two attractors in between, one attractor in between, 3 attractors in between, and then see what is the capability of my language model. So this is one way you can do analysis of your language model. Similarly, let's say I want to ask some questions. Say, how much context is essential for new language model? See, when you train an RNA language model, so one good thing was that I don't have to worry about a fixed window. That is beyond fixed window. So I can have a very long sentence or a document. I can have a document running across, say, 1,000 words. And I can keep on passing W1 or W1000 through a recurrent neural network. Yes. And I keep on predicting the next word. But fine, that may give you good performance. But now suppose you want to go back and ask, how much context is actually essential for my neural language models? How would you design such an experiment? Similarly, suppose you want to ask, do neural language models use the words in the context as back of words? Like, do they care about the order if I go beyond, say, 5 words? If I go beyond 5 words in the context for this, say, W6, or let's say W10. So these are W5 to W9, and they are W1 to W4. So for W10, how much does it care about the word order? Or is it that it is looking at all these as a back of words? It doesn't care about the order at all. So this is a question that you may like to answer. And you may like to see whether your language model is looking at the word order at all. And if it is looking at the word order at till what level? So how would you design an experiment? So first one is easy. How much context is essential for neural language model? What would you do to design such an experiment? How much context is essential for neural language models? What would you do? Think of a simple experiment. Something I want to make a plot saying, okay, uh, if I have this much context, that's sufficient. I don't need beyond that. So how do you measure the performance of language models? Said how good my language model is. The standard matrix is perplexity. And perplexity lower the better. This is like negative log probability. This negative log probability of observing the sequence. So it's lower the better. So I can plot perplexity based on the context set. And I can see when does it saturate. Okay. So experiments were done on this context size on two different language models, trained using Pantry Bank and trained in Wikipedia. And what you see if you keep on increasing the number of the context size. So yes, the you are learning up to say around 250 words in context. But beyond 250 words in context, you are not learning much. Okay, the loss remains the same. But if you so this is with respect to this 1,000 words, how much loss would increase if you take say 10 words only, the previous 10 words, and you see there's a huge loss. The loss is increasing by 0.3 if you are using only 10 words in context. But if you're using 250 words in context, your loss is not increasing. So you can say, okay, 250 words is what my language model is. So only giving it 250 words of context is sufficient. 250 words are good enough. It is using 250 words. But if I just give 10 words or 20 words, no, it increases the loss. So that means it is using much more context than 10 words. Like that, we design an experiment. Now, can you think of an experiment for the second part? So I want to know whether it is using the context as bag of words or it cares about the order. So the way you can design an experiment is, okay, I take my data set and I do something, okay. Once I go beyond the context size of say 5 words, I permute the word order, I change the word order, and let's see whether it has any impact at all on my performance. So what is done? So you shuffle the word order beyond a context. So this means beyond till the previous and next 5 words, I won't do anything, but say beyond 5 words of context, I shuffle the word order. Shuffle the word order fully. Okay, just shuffle the word order and see whether it is still able to make prediction correct. Okay, so So what was observed that yes, up to 50 words, it's fine. Up to 50 words, uh, if you shuffle the context, it is it's still having a loss. But beyond 50 words, if you shuffle the context, it does not change anything. So that means in the previous slide, what we saw, that language model is using 250 words context. But among these 250, for the 50 words, it is also using the word order. But from 50 to 250, it is effectively using them as backup words. And that is very interesting insight about language model. That came from such an experiment. So actually, there are many things about interpretability and all that I did not put here, but just wanted to give an idea. So this is how people capture this. They try to design experiments, and depend on the experimental output, they try to say certain things. Like I can say now that language models, they use 250 words in context. They don't use more than that. But among 250 words, they use the word order. Beyond that, they don't use the word order. So yes, so I just covered a few things for this. A lot of new tasks are coming up, and I think the focus more is towards harder problems now. For simple problems like part of speech tagging and named entity, we have already achieved good enough performance. So lot of focus now is in reading comprehension for harder problems. For example, I want to be able to answer questions from longer documents. So suppose you give me a court case filing that may be 50 pages long, and I want to do question answering from there. I don't have very good models for doing that. So can I look at harder tasks like question answering over a lot of very long documents? Or say multiple documents. Say maybe my answer is lying across multiple documents. I have to combine from them. And that may require multi-hop reasoning. I have to get some clue. It's like treasure hunt. I get some clue from one document, use that to get a clue from second document, and so on. And also a lot of focus now is on dialogue. So how do I have dialogue understanding, generate good and good dialogues? Because dialogues require you not only understanding of a long utterance that has happened, but also some background knowledge. So how do I do a good dialogue understanding? And second, very important focus is that, okay, a lot of people, see, all of us now, we have smartphones and other devices, and all these models people want to deploy on that can run locally on these devices. But immediately the problem is that all these models like BERT and all, they use so much compute, you can't use a pre-trained BERT and use it for doing anything on your mobile. So can I have models that do not use a lot of compute power? They can do the same, roughly the same accuracy with very small computation. So this has become very popular. Like model distillation has been one of the very important field. So I use some idea to distill the original large model into a small size model. And low data setting, we talked a little bit about that, but few shot learning has been one of the main trends. And at the same time, this meta learning has also become very popular. It has shown good results in the field of computer vision, and people have started applying it for NLP. And of course, whatever we said in the beginning is there, that yes, how do you go to a specific task, a specific language where you don't have sufficient data and apply these models. So yeah, with that, I think, yeah, this was what I had to say for today. So if there are any questions, I'll be happy to take.
Yes, any questions, please? In the audience. So if there are no questions, so let us thank the speaker, Professor Pawan. This is the second session he is taking for us. In the first session, he covered about sequence-to-sequence models. And in this session, he covered about the current trends where the context setting, transfer learning, something like interpretability, so on. So these are all giving us the future directions of the research. And I strongly believe that this will motivate us in doing the research in this NLP problems. So I would like to thank the speaker again for his valuable time given to us. Thank you, sir.
Thank you very much. Okay.
So to the audience now, I sent the afternoon schedule through WhatsApp group. There will be a simple assessment test will be there. The link will be sent to your email. So we will post the link in the chat box for the assessment test. So by clicking that, the form will open where mostly the objective type questions are there. It's very easy actually. So please attempt that one. And after that, we are going to have a small valedictory function. Okay. And you see that here we might be asking you to give us some feedback. So this is local feedback for us. Maybe orally you might be saying something to us. But actually, you have to give the feedback at the AICTE portal. So that is unknown to us. We don't know about that. So that is actually your feedback. And after giving your feedback only, you are going to get your certificate maybe after 2 working days. This is what AICTE is saying. So this is for your kind information. So if there are any quick questions, you can ask me now. The assessment test will be very simple. Write the assessment test because without that, you are not going to get your certificate. It will be very, very simple actually. If you are having any doubts or questions, please raise now. Who will be sending the link for AICTE feedback? No, the AICTE portal itself has feedback link. When you registered, you might have gone to the AICTE portal, right? Now, in the last day of the FDP, when you log in to the AICTE portal, there will be a feedback button will be there. So that button you can give, that button you can use to give the feedback. The important thing is that we don't know your feedback. Maybe AICTE after some time might give us the feedback from you to us. Okay, so it is anonymous for us actually. We don't know who gave the feedback, what feedback and all these things. Okay. Is it
Sir,
clear?
in email, when you will send the link and how much time we can take to complete the test?
Not in email, we will paste the link in the chat box.
Okay, how much time we will be giving?
1
1
hour.
hour.
It's 1
Okay.
hour. There are, it's for 25 marks. All are objective type questions. There, feedback? No. In the AICTE portal, feedback button is even now it is active because today is the last day, right? You can enter it, but we can't see it actually. The coordinator or the institute which is coordinating, we don't have access to that one. It is only for you and the AICTE. The link we are going to paste into the chat box. Exam will be for 1 hour for 25 marks. All of the questions, 90% or 95% of the questions are multiple choice questions. There are no negative marks. So if you can score out of 25, 15, that is the cutoff actually. So then you are going to get your certificate. but the test is simple actually. Okay.
Sir, the questions will be from the PPT you sent, sir.
Maybe related to whatever we covered, but they are covering some fundamentals only, not going into the depth of research and all these things. We're not
sir.
going into the research topics and all these things, but the fundamentals we are going to ask. Something which normally any person who is aware of the machine learning field will be knowing.
As usual, 60% is the pass percentage, sir.
Yes, yes, that is true. But
Okay.
you write the exam.
Okay.
Writing exam is very important. Only then the next step is possible.
Okay. Thank you, sir. The session was very much helpful for us. Thank you.
Thanks. So now let us close this session and we will meet at 2:25 or so. So at 2:30 we are going to begin the assessment test. Is it okay?
Thank you, sir.